So we're back for part 2 of volcanoes. I want you to look at this map and realize that a majority of volcanoes are associated with subduction zones, like along the Ring of Fire, like I'm showing you right in this boundary here and right in here. This would be the Asiatic belt right in here too. That's also a subduction zone. This would be a rift. So you can have them along divergent plate boundaries. I also see some divergent volcanoes along mid-oceanic ridges. An occasional one of these volcanoes will be located in the middle of a continent like Yellowstone or out in the ocean basin like Hawaii. And in both cases, that involves cooking of oceanic crust. But literally, a majority of all volcanoes are associated with subduction zones around the world, especially explosive ones. There are 3 basic body plans for volcanoes, and we're going to start with the largest of all volcanoes. But be careful when you're thinking about volcanoes and big and best and stuff, because you really need to be thinking about their total size, not just maybe what you see at the surface. That would certainly be the case for type number 1 called a shield volcano. Shield volcanoes have the total greatest relief. That means the bottom of the ocean floor is where they grow all the way to the top where we see them above water as an island. This is Mauna Loa, which is 56,000 feet tall. That's enormous. That's much larger, double the size of what you would think of with Mount Everest, or just a little bit over double. Now, shield volcanoes are connected to the mantle via magma chambers, like what we see in Yellowstone or Iceland. So these things typically have very mafic, almost ultramafic characteristics. So they're the hottest magma chambers we have and usually produce the least explosive of eruptions. This is a cinder cone volcano, which is type number 2. This is the simplest body plan of all volcanoes, and this is probably the typical shape that you would think of if you were drawing a volcano. Let's say if you ask an 8-year-old to draw a volcano, this is probably what they would draw right here. And so that's what most people think of when they think of volcanoes, unless they have a background or live next to a different type of volcano. This one's actually in Hawaii, and it sits on top of, interestingly enough, a shield volcano. So shield volcanoes can produce literally dozens and dozens of smaller types of cinder cone volcanoes. So I want you to see that it's a lot shorter and nearly as broad as you would expect to see a regular shield volcano to look at. So I want to point out that some of this clutter that you see on the outside of this volcano right here on Mauna Kea is actually volcanic bomb. So that tells me that this cinder cone has actually had some explosivity. This is a classic shot of the same volcano that I took in Hawaii. And you can see the classic cinder cone with the opening at the top, the crater. And if this were to erupt, let's say it would erupt this section out right here, you could have a pretty bad situation if a lot of lava could flow out. Let's say a town existed right where this sign is. They would be right in the flow of that occurring in Hawaii. This actually does happen in Hawaii. This is Mount Capulan in New Mexico. Capulan Volcanic Field sits in the Raton Pass area, and there were literally dozens of different volcanoes that existed back in the Tertiary, or what we would call the Paleogene of the Cenozoic era. So you're looking at some volcanoes that are very young in geologic history along a major rift. So if that area was pulling apart back then, and if you want the truth, it's actually still kind of pulling apart today. So very interesting topic. Now, your classic cinder cone volcano, and out in the distance you'll see what looks like used to be ancient volcanoes. There were some that were bigger than this that actually were composite types of volcanoes, but most of these were little cinder cone volcanoes that erupted lots of basaltic lava. Some, though, were a little bit more violent. How do we know that? You can look at this volcanic ash and see volcanic blocks. Remember learning about them in part 1? So that tells me by the character of the ash that this particular volcano was cooking through some continental crust, and these basaltic lava flows were probably almost intermediate, if they weren't intermediate, in composition. So let's learn about a special case study for cinder cones. This is Bandera Volcano and ice caves. Now, Bandera is a place we go on the geology field course, and it's one of my favorite stops on the field course, and just in terms of just a site we visit, simply because it's neat. It's just cool. This is a cinder cone volcano privately owned. How interesting is that? I'd like to be that person. And 10,000 years ago, approximately, this thing erupted. Now, going back a few slides, remember that volcano I said if it erupted the front of it out, that cinder cone, it can be dangerous. Well, that's what happened here. And it happened, and when it did, it blew out one flank of the volcano, creating lava flows a long distance away from the actual volcano itself. So we're sitting in, or looking inside of the crater. This is us on field course, the very first year we offered field course. So when you look at the volcano area, Bandera, this is another volcano not too far by that looks just like it, creates these types of lava flows known as flood basalts. What happened in Bandera was that these lava flows created lava tubes, just like we see in Hawaii. The only difference is they were in New Mexico and couldn't drain into the ocean. So the clutter you see on the bottom here is actually the volcanic top to those lava tubes that collapsed down. That's an important element because this is very vesicular basaltic lava. You remember vesicular means has holes in it from where air bubbles used to be. So this means that if rain or ice melt water can get and drain through this lava, it can get captured underneath this lava tube. Just like when it was hot, the lava tube will now insulate that water and keep it cold and literally below freezing temperatures. This is the ice cave itself, and the green stuff is the actual biological material that grows inside of, kind of like phytoplankton, algae material, moss, that kind of stuff that grows in the layers of the ice. And so this has been layered over a period of years, and that period of years has allowed us to create this massive amount of ice blocks since this volcano created the lava tubes about 10,000 years ago. Let's get into the most complex and dangerous in terms of eruption and violence of any type of volcano on the earth. That would be composite volcanoes. They have nicknames called stratovolcanoes. Most composite volcanoes grow along subduction zones because that's where we have blending of oceanic crust with continental crust. Occasionally you can get a supervolcano above a hotspot in a continent, which would be a rare circumstance like Yellowstone, but nevertheless they would be even more complex composites than any that you could see along a composite subduction zone. These have multiple conduit systems, so that means they can be hooked in and actually explode in many different ways and directions, which makes these very unpredictable when they explode. We learned our lessons with Mount St. Helens. You're looking at Mount Shasta, which is not but just a few hours away from Mount St. Helens in Oregon. And when I drove by Mount Shasta, Mount Hood, Mount Adams, Mount Rainier, Mount St. Helens on my sabbatical, I was blown away by the character of each of these volcanoes, knowing a lot about volcanism and volcanoes, seeing the string of them over the course of a week of travel along that stretch of land. I was reminded that subduction is real and that subduction creates some very dangerous. So we're going to do a case study of Mount St. Helens back in 1980. And when she erupted on May 18th, and talk about why she was so devastating. Mount St. Helens actually blew out the north base of the mountain, causing a massive rock slide, the biggest ever observed in modern history. Why did this happen? Let's go back to the lava dome that you learned about earlier. The lava dome on Mount St. Helens had actually filled with all of that viscous magma, and it was penned up behind that lava dome. There was a 5.1 Richter scale earthquake, which actually kind of uncorked the lava dome, causing the entire north base of the mountain to slide off. When that occurred, it literally unleashed a pyroclastic eruption that within 10 minutes buried 230 square miles of area and was buried by a pyroclastic debris flow. In addition, this eruption melted all the ice fields on top of Mount St. Helens and actually created a massive lahar. So when I visited Mount St. Helens on my sabbatical, I visited in June. And so there was lots of snow on the ice field at that time. So depending on what time of year you're there, more snowfall will be there and ice packs will be there than there would be in the dead of the summer. But composite volcanoes have one characteristic: they have tall elevation. And I was reminded of that on my sabbatical as I made that drive and saw all of those subduction zone volcanoes from the Juan de Fuca Cascadia subduction zone, and they all had that similar characteristic of ice fields at the top. So when she erupted on that fatal day of May 18th, the pressure behind this is the new one, but this section of the mountain right here completely blew out and created a massive landslide. So the eruption itself lasted for about 9 hours, but in that 9 hours, a series of really devastating things occurred, and subsequently it continued to erupt for days afterwards. That's not something that everybody talks about because there was other types of hiccups from the mountain after the initial eruption occurred on May 18th. This is what she looks like today. So you can see the ice field at the top, and mind you, this is June when I'm there. And you're seeing this modern day lava dome. Now all of this stuff you see is the landslide and the Lahar that just totally took out an old growth forest. More to come on your virtual field trip about that particular story. When the pyroclastic cloud blew, Mount St. Helens actually devastated this entire area. This would be some of the old growth trees in the background. This is what happened to those trees. The pyroclastic flow literally snapped them at their trunks. And this has been eliminated, this entire forest, within 10 minutes. Now, some animals actually survived the blast, which is almost incomprehensible, but they were burrowing animals or animals beneath the water surface where most of them were still capped by ice at that time, the lakes nearby, and animals that had found shelter inside the ground. But nevertheless, if you were above ground and you were in the blast zone, you didn't stand a chance. So the blast zone looked like this prior to the eruption. That's an old growth forest. They are now replanting the St. Helens tree farm to try to bring back the area that was devastated in the 1980 eruption back to its current state. So after the blast, you can see this entire section here used to be that same kind of wooded forest, and it was just totally eliminated in such a short, brief few minutes of time while this eruption took out that area. There was actually a silent zone where you could have been nearby the eruption or at the site of the eruption. There were hikers like on Mount Adams that saw the eruption but didn't hear it, which is absolutely flabbergasting to me. So eyewitnesses who lived to tell the story, who were 9 miles away from the crater when the mountain erupted, reported hearing the thrashing and snapping of trees but did not hear the explosion itself. The reason that occurred is sound waves at the site of the eruption had to bounce up to the stratosphere and come back down to the Earth's surface. So if you were in this zone, you wouldn't have heard the actual eruption, but you would have seen the actual event occurring. Kind of an eerie thought, isn't it? This is the Johnston Ridge Observatory, and Johnston Ridge is at the very top of the overlook that sees Mount Helens. And the reason it got its name, Johnston Ridge, is that's the last name of the volcanologist from the United States Geological Survey that was actually killed in the lateral eruption of Mount St. Helens. This is actually the Richter scale reading from the eruption. Right in here you can see these earthquakes, the 5.1 earthquake. And now this is a monitoring station along with other Cascadia range sites that monitor any kind of volcano action and seismic activity in the region. When Mount St. Helens blew off her lava dome, the pyroclastic flow inundated the area and buried the entire region in a fairly thick pyroclastic flow. These are the pyroclastic deposits, and we're not looking at an inch or two thick. These are multiple feet thick. So you're looking at a lot of stuff that was pinned up in that volcano and erupted with great force. One of the big stories about the Mount St. Helens eruption was the aftermath of a secondary threat called a Lahar. You learned about them earlier. These are mud flows. I want you to find the mud line on the trees right in here from the Lahar, and then find the person right here. And this is the Toutle River Basin, which I might add still flows today, but nevertheless it has a lot of problems because of the Lahar deposits that filled up that river. So it's been diverted and the river is cutting through these deposits, both Lahar and Pyroclastic. So this gives you a perspective of just how big this Lahar really was. There are 6 different types of eruptions for volcanoes. So every volcanic eruption falls into one of these categories. We're going to start with the least violent and work our way up to the most violent type of eruption. The least violent would be Hawaiian, and even then fissure, which is the next type. They often happen in tandem. But Hawaiian eruptions are very indicative of having basaltic mafic lavas that are very hot. They flow well. They create lava fountains, lava lakes, lava tubes, create hydrovolcanic eruptions like you're seeing here in Hawaii. This used to be a giant subdivision, and I found that odd when I took this helicopter ride and subsequently went by car out this area, because there was for sale signs everywhere for these houses that got buried, and actually going for a pretty good dollar figure and being purchased. That was the other mind-boggling thing. But I got this shot in a helicopter of a hydrovolcanic eruption occurring, and if you kind of look over here, you'll see a really dark black. That's the new black sand beaches that are forming. So a fissure eruption is the next type of eruption. They can be a little bit more explosive than Hawaiian, but they actually do happen in Hawaii, Iceland, anywhere where the earth will separate and make a fissure eruption. They're usually associated with mafic eruptions, so they're not very violent, but they can be if you're blending with some type of continental material. This is a rift that is in Iceland that I saw in 2012, where the earth is actually separating away. And this was one of our tour people. And as we were watching them walk, I just wanted to put them in scale with the rift so you could actually see that that's the site of where a volcanic eruption once occurred and was producing very mafic eruptions. All right, the third type is obviously more explosive. We've moved up into Strombolian eruptions. You should notice right away this looks a lot different, and this is why. There's a little bit more gas-charged particles there, and usually these, well, almost exclusively, Strombolians are mafic, but they're on that line that's getting closer to intermediate. And so you have a little bit more pinned-up gas, and they produce little hiccups and make beautiful fireworks displays of volcanic blocks and volcanic bombs. So this would be more explosive than you would see with a fissure or a Hawaiian. Stromboli is actually in Italy, and Strombolian eruptions are named after Mount Stromboli. So just like Hawaiian eruptions, Stromboli eruptions can occur anywhere in the world. They're just named after a place that is characteristic of them occurring regularly. Phreatic eruptions are completely different. Now you can notice right away that this is a lot of ash and material being shot out. There's actually a type of phreatic eruption that involves water that can cause a hydrovolcanic eruption to clear a volcano's throat. Nevertheless, most phreatic eruptions don't have much lava with it. If it does have considerable amount of lava, it's really considered the next type, which would be a volcanian. But phreatics are often the precursor to a very large volcanic eruption like we saw at Mount St. Helens, which is exactly what you're seeing right here. This was basically the volcano doing this clearing its throat before it has its major eruption. One of the most famous eruptions that's a phreatic is Krakatoa. It even sounds explosive, doesn't it? Krakatoa. In 1883, Krakatoa erupted, and I'll tell you she's still active today. But in 1883, she did a devastating thing because she had a violent phreatic eruption that was equivalent to a 100 megaton explosion. So this was a lot of force, and when she did, she emptied out her contents very quickly, collapsed the magma chamber roof, which made a caldera. Since that sank this entire region you see right here, it actually created a tsunami, or a set of tsunami waves, which killed a bunch of people on those islands, as you could imagine. So Krakatoa is a very famous phreatic eruption. This is actually Mount Krakatoa in 2007. You can see she's very much active, and this time you're seeing what looks like a pyroclastic flow down the side. So that pyroclastic flow represents a Volcanian eruption. Volcanian eruptions display phreatic ash clouds with lava in addition to it. So these can be very dangerous. You definitely want to keep your distance from phreatics and volcanians, and certainly the last type called Plinian. Which brings me to the final type, the granddaddies of all volcanic eruptions, called Plinian. You might wonder where that strange name Plinian came from, and I'm going to tell you the story. Plinian eruptions are the most devastating of all eruptions because they have the most force. They're usually associated with very big composite subduction zone volcanoes or something like Yellowstone mega super volcanoes. And they shoot up ash clouds like this one straight up into the atmosphere, usually tens of kilometers high, and produce pyroclastic eruptions on the ground. So these are extremely dangerous. When you think about Plinian, think of them being the most violent type of eruption on record, and they often produce calderas because of how quickly they empty out their magma chambers, which I find interesting that Mount St. Helens did not, even though she was a Plinian eruption, because that means she didn't empty out all of her stuff too quickly. Had it been a little bit stronger explosion, I bet you that would have happened. With the Plinian eruption, you usually would expect to have pyroclastic flows and even lahars because you're going to melt the ice fields like you see right here at the top of a volcano. Let's talk about where Plinian got its name and the most famous of all volcanic eruptions, Mount Vesuvius in 79 AD. So Mount Vesuvius buried the towns of Pompeii and Herculaneum. Let me point out that the towns of Pompeii and Herculaneum are not the volcanic event. So some people say, oh, it was Pompeii. They're referring to the city, not the event. Mount Vesuvius, however, is the volcano that erupted. What's interesting about this particular situation, let's give a little history and background. Here's Herculaneum, here's Pompeii. This is Italy, and you have to think back to 79 AD and the Greek Empire at that time, the Roman Empire. What was going on history-wise? These towns along the coastline would have been major port cities, capitals for better lack of words. This is where all the trade and all the important folks would do their work. The politicians would live. These would have been crowded, busy cities. So you need to imagine that Pompeii and Herculaneum were much like Austin, Texas, kind of giving you perspective. That's where everything was happening. All the port cities, everything coming in and out for trade, everything happened along those areas. Well, when Mount Vesuvius erupted that day, she put literally a cloud 20 miles high in the atmosphere. We have a manuscript from a gentleman by the name of Pliny the Younger. Pliny the Younger was actually successful in getting off of the area and into a cave to observe the volcanic eruption based on guidance from Pliny the Elder, who wanted him to live and be able to document this. So Pliny the Younger actually wrote a manuscript that was discovered, and because it was so accurate with drawings like this one right here about how the volcano behaved, how tall the ash clouds were, we as volcanologists actually, we as geologists gave him the credit for the name of the most explosive of all eruptions, Plinian. So Mount Vesuvius buried 1,150 casts that have been discovered thus far in Pompeii and Herculaneum. This is a very difficult set of images to look at once we see the cast of the humans. And you have to imagine that the actual eruption lasted most of a day, but it buried these towns in up to 75 feet of pyroclastic flow debris. So the people who were there didn't stand a chance. If they got in the pyroclastic flow, they would die. So you had to be away from the volcanic activity in order to survive. These are difficult images. Nevertheless, they are what's famous about Pompeii and the Mount Vesuvius eruption. Don't forget about Herculaneum either, but Pompeii got the blunt of the force. And how do we know that? It was a lateral eruption, it appears, much like Mount St. Helens, and it looks like a majority of the pyroclastic flow actually went more towards Mount Vesuvius than Herculaneum, meaning towards Pompeii than Herculaneum. Nevertheless, both towns were inundated with a very, very thick pyroclastic flow. I would suspect that some people died from suffocation before they ever had a chance to be killed by the flow like these people, but this not so lucky right here. And it's very difficult when you see that, because this would have been the scene happening probably the day of the eruption, before the big Plinian eruption actually unleashed its ash. People trying to scurry to get to safety, and then other people being not so lucky. Pliny the Younger's manuscript's very vivid, and it's difficult when you think about the devastation of these people. So I might want to correlate why that's so important, because we as geologists are really trying to protect human health and the environment. And Mount Vesuvius is a lesson that all volcanoes have potential to be devastating. So before we do VEI, why don't we take a short break? I think you guys have earned it. I'll see you back in a few minutes for part 3 of Volcanoes. Bye.